Okay, perfect. Close the transcript. Okay, we are ready. So you should see my website now, and let's go to the web page of tutorials of Harbour Engineering. Let's go here, and I just would like to remind you that in the past lecture we dealt with the first 3 links. They were essentially descriptive. Today we have something that is a little bit more technical, and here is the web page to which we make reference to. Let me just expand a little bit the font. Now today we get into forcing estimation and for Harbour design. It's of course a topical issue. It's a task where the engineer is called to operate according to the background precisely of engineering to make some computation in order to size, design the structures that compose a port, an harbor. Now, first of all, let me just make clear what are the kind of forcings that we focus on. Forcings means the actions. The actions, we can call them design variables, which need to be considered when sizing a structure. And there are several different forcings. You may think of forcings, as we discussed last time, from the seaside, forcings directly from the berth itself, and forcings from the land. We will not focus on quantitative estimation of forcings from land, and such as, for instance, soil pressure. We will not deal with these forcings. We will not deal with traffic load and other stresses on the berths that are induced by land-side processes. The reason why we don't do that is to avoid any overlap with other subjects. I think in geotechnical engineering, you are already focusing and discussing these forcings that come from the soil, for instance. I hope that also in road engineering, you are studying or transportation engineering, whatever is the title of your subject, you are studying the loads induced by traffic. We will focus on loads from the seaside because this is what is pertinent, relevant to this subject, or which is called Harbour engineering, as you know. So from the seaside, we discussed last time that we may expect several different forcings. Let me go back to the previous lecture because there is a figure that I would like to show you. This one, I think it is particularly meaningful. And in particular, we will focus on forces from wind and waves. And we will have a short discussion on forcing originated by currents. And the forcing means that we have actions that can act directly on the structure of the berth, or, which is more important, actions that are acting on the berthed ships, the docked ships. And then through the mooring lines, these actions are transferred to the berth structure through mooring, what are called mooring forces, which are, of course, which are acting on the mooring points. So this is what we will consider, and in particular, we will start with wind forcing, which is extremely relevant, and wind forcing is relevant when it is referred to the forcings that act on the ships, on the berthed ships. And we will focus also on wave forcing, which it is acting on both the ships and the berth structure. But let me just say and fix in our minds that the forcings that are acting on the ships and then transferred through the mooring lines to the mooring points are much more important than the forcings that are acting directly on the berth structure. Let me go back to the web page that we focus on today, which is here. Here you see a picture of a mooring point. It's called bollard. It's a mooring bollard. And there are several other pictures of this kind on the web. And in this case, it's not particularly meaningful. But when you have some doubt on some parts of the berth structure that may be not so clear to you, I think that the bollards are clearly known to you, but there might be some other part of the structures that are not so clear to you. I suggest that you refer to the web, look on the web for pictures so we can understand each other. Last time, for instance, for the fenders, in order to clarify what fenders are, I showed you some pictures. Most of what I am teaching today and is reported on this web page is taken by a publication which I highly recommend to you, which is the Port Designer's Handbook. And you see a link here in my website. Let me click on this link. You see my mouse goes over the link and let me open it. This is available as a PDF. You can find it on the web. This is on my website, taken from my, actually it's directly from the source. You see the URL, the web address here, marine men, etc., etc. And it is an interesting publication, which I consider still a very good reference for the international literature on Harbour engineering. And most of what I'm teaching, as I said, is taken from here with some changes. This is a publication of 2003, so it's not old, but still it's not very up to date. Keep in mind that science is progressing very quickly these years, and therefore a book that is 20 years old, okay, we cannot say that it's completely gone, but still it's not very up to date. In the past, it was quite usual to study at the university level on books that were 50 years old. Now it's a bit more, we need to be more careful because, as I said, the progress is advancing very fast. But still, I think that this book is still the best reference at the international level that you may find. It is very pragmatic, and it goes directly to the scope. You see that there are a lot of topics that are discussed here, starting from port planning. We don't discuss port planning. Maybe that you discuss something with Professor Archetti about port layout, etc., etc. And then there are the environmental forces. We discuss them. And then channels and harbor basins. We don't discuss this. We just focus on environmental forces. And as I said, I made some changes because I like also to take some different sources to refer to different sources of information, and therefore if you compare what is in the handbook with what is in my website, you may find some differences. And then you see there is another chapter on berthing requirements, and then impact from ships. We don't discuss this, but actually it is an important forcing that may act over a berth. The impacts from ships, which can be classified as ordinary, let me call them this way, impacts, which means that any time that a ship docks, of course, there is an impact between the ship and the berth structure, which is in a way softened by the fender, but still there is an impact. And there are exceptional impacts, which are caused by accidents, by mistakes in maneuvering the ship, which indeed may be the source of important forcings. We don't discuss these. And the reason why we don't discuss this is that it is also discussed in other subjects. The impacts of ships against berths are similar to the impacts of cars against road infrastructures. So I don't think we really need to focus on this, but just beware that this is another forcing that we don't discuss, but it's still important. And then there are the described here design considerations. We will discuss some of them, like the design life we already discussed last time, safety consideration, and also there is a chapter on types of berth structures, which we already discussed last time very briefly. Here it's more extended. Gravity wall structures, open berth structures, and etc. And also there is something particularly dedicated to fenders and to very specific details of the berth structure. Now, I'm not saying that you have to study this. I'm just drawing your attention on this reference because I think it is something that may be very useful in your future if it happens to you that you have to design an Harbour. Okay, let's go back to my website. Last time I gave an homework to you, which was to take a look to the glossary of nautical terms, which you can find in this link that I opened directly from my website. And you see here there are a lot of explanations with examples for some of the most used terms that we could find during our study. And again, this is not to be studied, but keep in mind this reference because I found it very up to date and very useful. And okay, this is okay. And just let me close this. There is a box on nautical terms, which I already suggested to you to learn what they are, because at the exam there might be some questions on this. And in particular, the terms that are indicated here, please learn what they are, because we will find them several times during our discussion. So the beam, I am emphasizing and highlighting these terms while I speak. Length overall. So it may happen that you get a question at the exam like, can you please tell me what is length overall? Or I may ask you to draw a sketch of a boat and show by drawing what is the length overall, waterline length. Length between perpendiculars, this is extremely important. And the draught or draft and the freeboard. Okay, here you see freeboard is F if you look at the bottom figure, and the draught is D. Very good. So keep in mind what is freeboard, what is draught. Today we will find this these terms. Okay, now just let me look for the pen of my graphic blackboard, because I wanna now start drawing something on the, okay, here it is, drawing something on the graphic blackboard, because it's more interactive. If I just read the website like I did last time, it's not very interactive. Okay, so let me share the screen and pass to the graphic blackboard. Just give me 1 second. Okay, and I share again. Okay. Here we are, perfect. Okay, now you should see my graphic blackboard now. So let's talk first about, and let me just go here. Okay, let's talk about mooring loads. Okay, mooring loads. Perfect. And first of all, what is a mooring system? A mooring system, it's something that allows, just 1 second, a mooring system. It's something that allows us to dock a ship and keep the ship safely moored to a pier under specified design loading conditions. And you already know that there are normal conditions and exceptional conditions. And as we said, environmental forcing on a moored ship causes mooring loads, which are very important loads. They are the main, as I said, forcing that we have to consider to design a berth structure. These mooring loads may take place for direct contact between the ship and the berth, or through the fenders, or through the mooring lines. What are the mooring lines? They are the ropes that we fix to the mooring point, to the bollards, and to the fixed point over the ship, in order to, and we tension these ropes in order to safely fix the ship at the berths. And you understand that we have several mooring lines. If we want to keep the ship fixed, we need several mooring lines. Okay, we will consider in particular, when we talk about mooring loads, we talk about loads caused by wind, loads caused by waves, and loads caused by currents. Okay, these are the three items, the three types of mooring loads that we will consider. Okay, first of all, let me give you some rules of thumb in order to give an idea of what these mooring loads may be, in order to give you an order of magnitude. As I said, orders of magnitude are extremely important for an engineer. You have to get an idea in your mind of what is the amount of a mooring load, the order of magnitude. Okay, so as a rule of thumb, we can say that if we have a design ship of about 20,000 tons, then the order of magnitude for the mooring load is horizontal pull about 10-100 tons, depending on the ship displacement and the type of load, of course, because as I said, there are these three types of load: wind, waves, and currents. So the range, I mean, it's extended. Don't be surprised by the fact that I give a range from 10 to 100 tons. It's okay. And the vertical pull may be something about 0.5 the horizontal pull. These numbers are given in my website. You don't need to take notes. Okay. So these are the order of magnitude, and you know, the pull load should be considered occurring at any single point. This is what we are at any single mooring point. This is what we may expect from a berthed ship. And also, you know, you have to assume that these loads may happen at the same time in over all the mooring points. And the mooring, what is the spacing between mooring points? Actually, they are located at a distance that may vary in the range of 15-30 meters. And when we consider the load over the berth structure, we usually transform this concentrated load into a distributed load. Even if the load is concentrated in the mooring points, usually we assume that it is uniformly distributed along the berth structure, especially if we don't need a very detailed assessment of the load at fine spatial scale. I mean, if the structure is massive, it's extended, it's complicated, meaning that the design is takes into account, considers solutions of complicated structures, then we may need to be very specific and estimate the load at each mooring point and consider the overall load as a sequence of concentrated loads. But usually we talk about structures that are fairly oversized, gravity wall structures, structures that indeed can be designed with a simplified approach. And in these cases, in many cases, as I said, we can consider the load as a distributed one. If you have a design ship that is heavier than 20,000 tons, of course, these limits may be exceeded, and keep into account that when the weight of the ship becomes very important, then you may also need to assume to take safety factors that are important as well, meaning that if you have a tonnage of the ship that is a weight that is not really massive, then you can assume that not all the forcings are occurring simultaneously, like wind forces don't occur simultaneously with wave forcings. But if you have a huge ship, a ship that has an important weight, the concurrency factors need to be in a way adjusted in order to be able to consider that in some extreme cases we may have concurrency, we may have superimposition of several different loads. Let's start then with the wind forces. And I'm talking about forces on moored ships. Okay, good. They act on the body of ships. And let's say that they are generally more important than the forcing originated by waves. As I said, the forcings that act on the ships are more important than the forcings acting from the seaside directly on the berth structure. And when we talk of forcings acting on the moored ship, usually the wind forcing is an important one. And in order to estimate wind forces, you understand that there is a first thing that we need to estimate, which is wind. We need to estimate wind, and then we do what we call the characterization of wind. And basically what we need to estimate is a wind speed in normal and exceptional conditions. Good. What can we use to estimate wind speed? We use data, of course, and so we use wind data. Let's hope that these are already available. And if they are already available, and they are already available in important locations, so for important harbors, important ports, or for airports, usually you have already data available. If you design a new and maybe small harbor in a location that is remote, then maybe that you don't have wind data. And in this case, you have several different solutions that you can adopt. The first one is, for instance, to install an anemometer, which is the instrument measuring wind. And the second one is to borrow data from a close-by location. So if you have data in another port which is fairly close by, and you have enough information to conclude that the wind behaviors are similar, you can borrow data from the close-by location. But now let's focus on the assumption that we have data. And if we have data, usually the data for wind data for nautical use and Harbour use are expressed through the Windrows. Now, let me show you Windrows. Let me just put an image here in my graphic blackboard. Okay, this is a Windrows. Let me just expand it a little bit. Okay, let me just check. But I think it is visible to you. This is in my website. I copied the picture from my website. And okay, here it is to expand. Sorry, I found it. This is a picture from my website. And precisely this is the Windrows of the LaGuardia Airport in New York. So how to read this? Let's spend some minutes reading this graph. When we talk about wind data, there are two features that we need to consider in order to estimate the forcings. The wind speed, which I already mentioned, but there is another feature, which is the wind direction. So any observation that is collected at an anemometer consists of speed and direction. Let me just put on the graphic blackboard a picture of an anemometer. Just 1 second. Okay, this one is perfect. 1 second, I get it. And let me put it here. This is an anemometer. Let me just move it in order to. Okay. This is an anemometer. As you see, there is a rotating part of it around a vertical axis, which serves to measure the speed. And there is also a sensor to estimate the direction, which we cannot see here, but just let me see if I can find a more detailed picture to show you how the direction is measured. 1 second. Images. Let me look for an image that is more meaningful. Okay, it's quite slow, but while we wait, let's just focus on the fact that in any case we get these two informations. Now, how is the observation of speed and information embedded into the Windrows? And I found the picture that I wanted to show you. This is the picture. You see, this is an anemometer where there is the rotating part of it, which is similar to what we saw before. And this is measuring the speed. And also there is the directional sensor on the right of the picture that through this rotating instrument, we can estimate the wind direction. And please pay attention to the fact that these sensors are wired. It means that there is an automatic transmission of the observation. Okay, let's remove this. And now let's focus on the Windrows. How to read it, as I said. Let's focus on the south direction, which is the prevailing direction of wind. This is the first thing that you get from this rows. You see that there are some directions where we didn't detect significant wind because the bars, the corresponding bars, are shorter. In the south direction, we have the longest bar, which means that this is the prevailing direction. But first of all, let me focus on the light blue circle in the center of the rows, where you see the indication of 3.6%. This is the percentage of time where we had calm situation, no wind. And this circle, of course, is not associated to any direction. No wind means no wind, that's it, in any direction. So 3.6% of the time we have no wind. Now let's move in the south direction and let's see that there is a first dark blue bar. Look at the legend on the right. It means velocity of the wind up to 3 meters per second. Okay, and you see that this extends up to about 2% of the time. So it means that 2% of the time we have a wind from 0 to 3 meters per second in the south direction. Good. Let's look at the next step of the same bar in the south direction. It's a dark green. It is extended from 2% to 8%. The difference is 6%. The dark green is wind from 3 to 5 meters per second. I can say that for 6% of the time, I have a wind in the south direction with velocity between 3 and 5 meters per second. Now, last step. It is extended from 8% to 12%. It's light green. Light green is wind from 5 to 10 meters per second. And the extension of the light green step is 12% minus 8% is 4%. Okay? So, of course, I rounded these estimates. So, conclusion, in the south direction, I have 3.6% of the time, zero wind. 2% of the time, wind up to 3 meters per second. 6% of the time, 8 minus 2, wind in the range 3-5 meters per second. 4% of the time, we have wind from 5 to 10 meters per second. What is the sum of this percentage? 3.6 plus 2 is 5.6, plus 6 is 11.6, plus 4 is 15.6. It means that overall, in the south direction, we have wind 15.6% of the time, including 3.6% of the time of no wind. I hope this is clear. This is the way you should read this Windrows in the south direction. Now, let's focus on the west direction. You can apply the same reasoning, 3.6% plus, and you get a percentage of time during which you have wind in the west direction that is lower than the percentage of time we found the wind in the south direction. Now, if in the south direction I said I had wind 15.6% of the time, if you sum for all the directions of the Windrows the percentages of wind in each direction, you get precisely 100%. So basically you have wind data and you estimate the percentage of time during which you have wind along a certain direction and within a certain range. And of course, if you cover the whole range and the whole directions, the whole set of directions, you get 100%. This is the way you should read the Windrows. And I mean, it is nice. It is a nice graphical way of providing a picture of the wind behaviors of the site. And you may say, yeah, it's a little bit difficult to understand, but once you understood it, you have you get the advantage that any graphical representation gives. What is the advantage? The advantage is that it is immediately understandable. It gives to you a comprehensive picture, and this is what we need, and this is what also people that drive the ships they need, because they when sailing a ship, especially if it is a sailing ship, sailors, what they need is to get an immediate and comprehensive perspective of the wind they will find. So this is wind characterization. And if you think to the information that the Windrows gives, this information is expressed in percentages of time during which we have a certain event, wind in the south direction, for instance. This percentage of time, you can call it frequency. Okay, you can call it frequency of wind in the south direction. It is a little bit more technical term, because percentage of time maybe is easier to understand. This is why I used percentage of time to introduce this discussion. But you can say frequency, it's the same thing. And let me say frequency is something that, yeah, people understand. But if you now switch to a more mathematical reasoning, what is frequency? It's an estimate of the probability of something. If you think something that has a high probability, what does this mean? That it happens frequently. It happens frequently. So frequency, it's a concept that is close to probability. So we moved from percentage of time to frequency to probability, with an increasing level of technical meaning. Percentage of time is not very technical, frequency is technical, probability is very technical. And so what can we say? We can say that the Windrows, which gives an estimate of the frequency of something happening, is providing an estimate of the probability distribution. Now, I am not sure if you had already in your background some education on probability and statistics. I am sure that the answer is yes. I'm not really sure if you remember what is a probability distribution, but let me show you then a picture of a probability distribution, but a picture that refers to the Windrows of LaGuardia. So this picture, what gives to you, I anticipate, and then I will show you on my blackboard. It gives to you the probability distribution of the wind in the south direction, which is what we discussed before. Now let me remove, let me just keep the Windrows, and let me put this figure, just 1 second, I expand it. This figure here, just 1 second, because actually I want to be able to 1 second. First of all, let me just remove these writings because they take your attention. Let me try to okay, very good. I am cleaning the blackboard, otherwise, you know, it's not so nice. Very good. Okay, here we are now. Let's okay, and now let me try to paste the other figure. Okay, and now let me move this. Okay. One second, because I have a minor technical problem with the blackboard. Just give me a second. I don't understand why it doesn't respond to. Okay, very good. I succeeded. Okay, so you see these two figures now. Let's focus on the south direction, and let's focus on the red line on the right. It starts at wind velocity 0. In the horizontal axis, you have wind velocity, and on the vertical axis, you have percentage of not exceedance over all the directions. So we start from 3.6 here. Let me just we start from here. This is 3.6, okay? And then if we go to a wind velocity of 4, a wind velocity of 4, it's more or less in the middle of the dark green part. What is the percentage of time where we find the wind velocity up to 4 meters per second? Is 3.6 plus 2 plus something like 4%, so it's about 8%. And we find this point. If we go to 12 meters per second, which is the dark green, we said before that we are around 15.7%. So this is the last point. So this is a distribution of frequency. And frequency of what? Frequency of not exceedance of the wind velocity. And it's a distribution of frequency. It's a distribution of probability. Because, as I said, frequency gives an idea of the probability of something happening. Very good. Now, you know that when we estimate the design variables, sometimes we need to use probability. I think that you are already familiar with the estimation of extreme wave height. And the estimation of the extreme wave height is done for a given return period. The return period is precisely, we will discuss this later, a translation of probability. Therefore, we need to get familiar with what is a probability distribution, the concept of probability. And this is why I am making this discussion. This is why I translated the notion of percentage to the notion of frequency and the notion of probability. Because I want to tell you that a probability distribution is nothing more than a graphical tool that gives to you an estimate of the percentage of time in which during an observation period you observed a certain event. This is the probability distribution. It's a graphical tool that can be expressed also in analytical term that gives you an estimate of the percentage of time, I repeat, during which in a given observation period, like 10 years, you observed a given event happening. So it's not really, it is very technical. It's not so difficult to understand what is a probability distribution. And the Windrows is giving us the probability distribution of wind data along each direction. And so passing from the Windrows that you see on the left to the cumulative probability distribution or probability of not exceedance, I said, on the right, is extremely simple. You just go along the south direction and you sum the percentages of time during which you observed certain wind velocities. I don't think that we need to give more details about probability because you already studied something, probability distribution. I think that you know the Gamble distribution, for instance. But before asking you if you have any question, I want to draw your attention on a box in my website. And now let me share the screen on my website. Here we are. You see that in the same page, you see the Windrows and then the picture of the probability distribution and this box, probability. So let's try to read, because I kindly ask you that you read this box and you study this box, because it is true that we don't need to go into the details. But as an engineer dealing with Harbour engineering, you need to be able to provide a definition for probability. And you have to have clear in your mind what probability is, what is a probability distribution, what is a probability density distribution. I don't want to go into the details, but because I don't need them, but you need them. Because, I mean, it is extremely, I think it is important that I highlight to you what are the essential concepts for your profession, because it is not a good thing if you go for a job interview or if you discuss with a client and you miss some important concepts. So let's have a look at this box. And as I said, it is quite short, but please learn what's written here, because at least because I could ask something at the exam and I will be clearer while we read. So probability describes the likelihood of an event. And I think this is already clear in view of the discussion that we had. Probability is quantified as a number between 0 and 1. This is the way probability is quantified, where 0 indicates impossibility and 1 indicates certainty. I think you may have used these expressions of common language, like the probability of this is 0. The probability that I become president of the republic is 0. Or the probability that something will tomorrow will be another day is 1. It is certain. We are certain that tomorrow is another day. Keep in mind that in our everyday life, it is more likely to experience something that it's not certain with respect to something that is certain. But still, I mean, also it's important that we have clear in mind what is the concept of certainty. The higher the probability, the higher the likelihood that the event will occur. And now, how can we define probability? We said it is between 0 and 1, but how can we define it? I think the best way is through the 3 axioms that you see on the screen. They are the Kolmogorov axioms. So axiom 1, the probability of an event is a real number greater than or equal to 0. Okay. Axiom 2, the probability that at least one of all the possible outcome of a process or an experiment, such as rolling a die, will occur is 1. I mean, I make an experiment, I roll a die, I toss a coin. The probability to get at least one outcome is 1. Okay. If two events, axiom 3, A and B are mutually exclusive, then the probability of either A or B occurring is the probability of A occurring plus the probability of B occurring. These are the three axioms. Okay, let me translate with the example of tossing a coin. Axiom 1, the probability to get head or tail after tossing a coin is greater or equal. No, sorry, axiom 1, the probability of an event is a real number greater than or equal to 0. Okay. Axiom 2, the probability that by tossing a coin I get either an head or a tail is 1. I think we agree that it's impossible that the coin will land just in between an head and a tail. Axiom 3. After tossing a coin, we get either an head or a tail, and therefore the two events are exclusive. Okay, either if one occurs, the other one doesn't occur. Good. Then the probability of either the head or the tail occurring is the probability of the head occurring plus the probability of B occurring. Okay. This is very simple, and then you can estimate probability in several different ways. You can estimate probability even by perception. So you can say, I think I have the same probability that after tossing a coin, I get an head or a tail. You think that, fine, but make sure that your opinion conforms with the three axioms. In this case, in the example that I gave, yes, it is. So how we can estimate probability? We can estimate it through an objective analysis of experiments or through belief. So we can make experiment or we may go through belief. Let me make an example, again, tossing the coin. I can make an experiment of tossing several times the coin, and then I count the number of heads, I count the number of tails, and then I, through the frequency of each one of them occurring, I estimate the probability. You know that a famous statistician, Pearson, in order to prove this statement that I already made, in order to prove that probability can be estimated through an experiment, he decided to toss the coin 24,000 times, and he got head 12,000 plus 24 times. He wanted to prove that this is a good way of estimating probability through experiments. So what is the probability of getting an head? 0.5. But you could get the same estimate through belief without making the experiment. So I can say it's clear. If I toss a coin, the probability of getting the head is 0.5. I don't need to toss it 24,000 times. But still, you define probability in two different ways. In the first case, through an experiment. In the second case, through your belief. The first way you used is what we call the frequentist definition of probability through experiment. You make experiment and estimate the frequency. It is the method that we choose for the Windrows of the LaGuardia Airport. We analyze the data. Analyzing the data means making an experiment. If you go by belief, this is called Bayesian definition of probability. And basically, it is carried out by estimating probabilities on the basis of your preliminary knowledge. Sometimes you cannot make an experiment, and then you need to go by belief. Like, for instance, when we say probability of winning an election, you cannot make an experiment. You cannot repeat the same election 1,000 times and see what is your probability of winning. You go by belief, and you talk to people and you get their opinion, like exit polls. You know, when there are elections, people try to predict the final outcome through exit polls. Okay, that's fine. And this is estimation by Bayesian approach. I want that you know these terms for the very reason that I mentioned before to you. Sometimes it happens very frequently that you get some people saying, I used Bayesian probabilities. So you know what they mean. Or like, I made an experiment to estimate probabilities. You know what they mean now. Okay, and you may tell me, but what is the, you may ask me, what is the advantage of one method over the other, frequentist versus Bayesian? There is no advantage. I mean, it depends on the event that you are studying. If an event is lending itself to an experiment, to a good experiment, then you may use the frequentist definition. If there is no way of making any experiment, then you can use the Bayesian approach. Look at the screen now. What is a probability distribution? And I just want to give you the reading of the first statement. A probability distribution or probability function assigns a probability to a considered random event. So, I mean, don't be concerned, don't be scared when people say probability distribution. Usually when this term is evoked, one thinks about complicated analytical relationships. You don't need to be concerned. It's just a function that gives probability to a considered random event. So basically, for tossing a coin, the probability distribution is nothing else than a function that gives 0.5 to the head and 0.5 to the tail. Now, what follows here in the box, it's the explanation of the difference of the concept of probability distribution for discrete versus random versus continuous variables. And let me just explain why we need to consider this difference. If you think at all the examples that I made so far, tossing a coin, rolling a dice or a die, it depends on the English, and on the American versus US English, you can say die or dice. So if you roll a die or you toss a coin, the result of the experiment is a discrete random variable. When we toss a coin, it's head or tail, is discrete. In this case, it's binomial. You roll a die, the outcome is either 1, 2, 3, 4, 5, 6 discrete variables. It's easier to talk about probability because the number of possible results is finite. It's the number of the possible results for the dice is 6. It's a finite number. But we talked about wind speed. We are talking about wind speed. This is a continuous random variable. When you take a wind measurement, you have infinite possible outcomes. So the concept of probability distribution is more difficult to be defined. I am not interested in going into the details of the difference between probability distribution for discrete versus continuous variables. I'm not interested in this subject. So this is something what you see now on the screen. This is not something I will ask at the exam. But if you're not familiar with terms like probability distribution for a continuous variable probability distribution for a discrete variable, probability density, cumulative probability distribution. If you are not familiar with these terms, I highly suggest you to dedicate a couple of hours to get familiar with them, so that you know what is the difference between a probability density distribution and a cumulative probability distribution. Because I mean, in engineering, I think you really need to know these, not for passing my exam, not for passing my exam with full satisfaction, but for a job interview, for these are very classical questions that one may ask at an engineer. Okay, very good. So what you read in the continuation of this box is again something that you don't need to study for my exam, but I take this opportunity because I forgot to say this. Another term, Gaussian or normal distribution. If you don't know what is a Gaussian or normal distribution, I suggest that you have a read, because you know it's important. Okay, now let me go back to my graphic blackboard, and then let's share the other screen. Here we are. Okay, let's remove the Windrows. Now we know what is, and we can read it. Let me see if I can remove it in this way. No. So let me just do this. And let's also remove this. And let's remove this writing that I didn't delete before. Very good. Okay. Now let me copy this picture to show on my graphic blackboard. Here it is. Let me expand it. Just 1 second. Okay. Have some problem in. Okay, now let me expand this, because otherwise. Okay. Can't magnify it. It's really sometimes. Let me check. Okay, very good. Okay, I think that I have to choose another solution for this. Let me just do this. Give me 1 second. It's better if I show it on the website directly. Okay, this is the figure that I wanted to show you. In this way, I cannot draw on it, but that's fine. Okay, so what is this? This is what is called the Bofford wind force scale, and it is introducing another series of terms that are very useful to you. It is a classification of winds basing on their velocity, from calm, 0, light air, light breeze, gentle breeze, moderate breeze, fresh breeze, strong breeze, near gale, gale, strong gale, storm, violent storm, hurricane. And this classification, as I said, is called Bofford wind force scale. The velocity is given in the bottom horizontal axis in meters per second, and in the upper horizontal axis in knots, which is a unit that is frequently used, as you may know, in nautics. Perfect. This classification, which is presented also in a link in a Wikipedia page that is linked from my website. And there is an interesting picture here. This is an image of a ship in force 12 storm at sea. You may have heard in some movies like we got a wind with force 10 or a force 10 wind. So these terms, force 12, force 10, refer to the Bofford wind scale. Okay, very good. And now let me emphasize another important concept, which is the Gust factor. So now let me go back to my blackboard. Okay, so what is one second. What is the Gust factor? Okay, it is the ratio between a peak wind gust and mean wind speed over a given period of time. So, a ratio between a peak wind gust and mean wind speed over a given period of time. Good. So when you have only measurements of mean wind speed, maybe over a 30-second time span, the Gust factor allows us to assess the peak wind speed. When you get wind data, in the metadata, so in the description of the behaviors of the data, you will be given the time scale, which is the period over which the wind is measured. Very precise instruments can measure over a period of about 2 seconds. Ancient or older instruments gave the estimate of the wind speed over a minute or over a full hour. So if you have a measurement, one measurement per each hour, the question is, what is the peak during this hour? And you get the peak through the Gust factor. And the Gust factor is like, I would say, for an engineer, broadly speaking and roughly speaking, you may say that it's a safety factor. It is a multiplier. It is a multiplier because the gust speed is always higher than the average speed over a certain period of time. So just keep in mind of the Gust factor, which is something that you find in guidelines, in legislations for making the design. And now let's talk about wind forces. So we got an estimate of wind speed through the probability distribution. Remember, the Windrows gives you the probability distribution. And then you can estimate the wind speed, so the max wind speed for a given probability. So let's make a scheme in order to summarize what we discussed today so far. We have 1, the Windrows, which gives probability distribution. Good. And then you have guidelines or legislation for design. Give you what? The design probability. What is the design probability? The design probability is a prescription that says that you have to estimate the wind forcing for designing the berth by adopting a probability of 90%. What does this mean? It means that somebody may tell you through legislation guidelines, you have to estimate your berth to resist to a wind that happens only 10% of the time. If it happens only 10% of the time, it is a strong wind. If it happens 50% of the time, it is a lower wind. If it happens 100% of the time, it's very low. So they give you the design probability. And very often the design probability is given in the form of return period. Return period T. The design probability is P. What is the relationship between P and T? We will discuss it later, but the relationship is P is T minus 1 divided by T. To be discussed later. Okay. And I just want to tell you that when you read about return period, it's the same as probability. Okay, you have a direct relationship relating return period and probability. Very good. Now, if you put together the probability distribution and the design probability, you get the design wave. This is what we are. This is where we are. Okay. And now, sorry, the design wind, not the design wave. Let's. Sometimes I now realize that I mixed the terms, but for the concept that I wanted to deliver, it's the same thing. But let me just write here wind, because the same reasoning is done for waves. Once that you have observations, you can estimate the design wind or the design wave with the same methods. So this is why I made a little bit of confusion. But this is to be discussed later, this specific relationship. Just keep in mind that legislation gives you design probability or design return period, and then the Windrows by enter gives to you the probability. So by putting the two things together, you get the design wind. Okay, now that you have the design wind, so 3, the design wind, let's put it here, Gust factor, if needed. And then you end up with design wind velocity. Good. Okay, but now, once that you have the design wind velocity, how do we compute the wind forces? You may understand that wind is dangerous when it hits a surface. In our case, we said wind is dangerous because it hits a moored ship. And then through the mooring lines, I have mooring forces. Okay. Now, you can understand that there are, by intuition, several let's say, features to be considered in order to estimate wind forces. Once that we have the design wind, what are the features that determine the wind forces? First of all, the surface of the ship. If the ship is huge, there is more surface that is heated by wind. Second thing, wind direction. If the wind is orthogonal to the side of the ship, you understand it's a worse situation with respect to the wind hitting the ship not orthogonally. Okay, if it is the wind is along the longitudinal direction of the ship, there is a smaller surface of the ship that is exposed. Good. This is a second issue that is important. And Another issue that is important to understand is whether or not the ship tends to rotate. If the ship is just pressed against the berth or pulled from the berth on the seaside with no rotation, is a better situation with respect to some pull plus rotation. Let's try to have a look at these details. And let's first of all say that the area exposed to wind, we call it the windage area of a ship. And we say usually we make reference to the windage sided area. So the area exposed to wind on the sides of the ship, which is, as I said, important, extended. Okay. And now, when is wind a problem for the berth? When the wind forces become a problem, I give to you another rule of thumb. If force of the wind is up to 4, usually no problem. Okay. What is force? Force 4. Force 4 is in the Bofford scale is moderate breeze. Okay. Good. And another important issue to consider, which another important feature to consider, which I didn't mention before, the ballast condition of a ship is much important. And let me show you an image here. One second. Let me show you. Let me show you another page on the graphic blackboard, and let's try to, let's see if I can expand it this time. Not really. I think in some way I can do that. Yeah. Okay, very good. Now you can see a cross section of a ship with a ballast tank. So what is the ballast? The ballast is material that is used to stabilize the ship, especially when the ship is not loaded. The absence of load causes the ship to raise, and if a ship is very high over the water level, it is unstable. It is more exposed to wind, and it may become unstable. This is why some ships, when are unloaded, need to load ballast. Ballast is let me call it artificial weight. Usually is obtained by loading water, and therefore the water is loaded in a tank, which is called ballast tank, and the ballast condition is extremely important in order to compute wind forces, because the windage area depends on the ballast conditions. And therefore, this is typical of ships that are moored, and they have to, suddenly they have to resist to a strong wind. They have two solutions: either to undock, so to leave the port or the harbor, or to load ballast, because if they load ballast, they become more stable, and they are less exposed to wind. And also, given that they are more stable, the transformation of wind forcing in mooring forcing is more favorable. So for the same wind forcing, you get less mooring forcing when the ship is loaded or in ballast. So,
sorry, Professor.
Yeah, please.
This is due to the fact that the weight drags the hull more underwater and there is less surface.
Yes, this is the first reason and the most important one. But if you think also at the stability of the ship is more stable. So basically, you are less likely to get rotations in around the vertical axis, and also rotations, I don't remember the term, I will explain it to you later, around the longitudinal axis. You have less, and then when you have less rotation, you have less mooring forces.
Okay.
Did I answer? Perfect. And I just appreciate very much if you step in when you have any question for me. Please don't hesitate to step in when you have any question on that. Okay, and now, so how can we compute the wind forcing? And let me just write to you the relationship. First of all, the relationship that I'm now writing is physically based, meaning it makes reference to physics, and we will see, but it is essentially an empirical equation. It is an empirical equation because you will see that there are some coefficients. This happens quite frequently in Harbour engineering. Very frequently we use empirical relationships because we are talking of processes that have a significant random component. We are talking about wind. Wind is a random process. When we talk about waves, it's a significant random process. Randomness implies uncertainty, of course. I mean, but keep it in mind. And then we have a lot of uncertainty in our design. The presence of uncertainty, in a way, makes empirical relationships necessary. Because in a way, you have to find an approximate model to manage uncertainty. And this is why we introduce these empirical relationships. What I'm writing now in order to estimate the wind forcing is something that you will see it's physically based, but at the same time, you recognize that there is a lot of empirism in it. Now, let me write it. I take a black color, just 1 second. So let's call the wind force in kilonewton PW. We write it, and it's on my website, so you don't need to take notes, as the product of several factors. The first factor, we call it CW, is called wind force coefficient and is estimated empirically. So you see here you have a first reason of empirism times, let's open a parenthesis, AW. What is the AW? It's the side area of the ship above water projected over the ship longitudinal plane. I guess you understand what is the longitudinal plane of a ship, but I have a figure later on, so just give me some time. AW, side area of the ship. Perfect. Now, times sin square of an angle which we call phi. What is this angle? It's the angle between wind direction and ship center line. So let me try to make a sketch to better explain. If we have like, let me take another color, a berth here and a moored ship here. Okay, this is the longitudinal axis of the ship. Or ship's center line. Now, if you have wind hitting the ship along this direction, this is, sorry, phi. Okay. you understand that I multiply times sin square for two reasons. The first, sin is introduced in order to compute the projection of the side area, of the side windage area over a plane that is perpendicular to the wind direction. And this is why I have this sin that is introduced. And I have a second multiplication, another sin to estimate the component of this forcing that is indeed perpendicular to the side direction. Let's add here, sorry, let me go again to the black color. Plus BW. What is BW? It's the front area of the ship above water projected over the ship transversal plane. 1 second, I need to remove. Okay, in square meters. And again, let's multiply this times cos square phi times gamma W. It's the specific gravity of air, and it is a constant at a given temperature is a constant, times v, the wind velocity, VW square divided by 2g. And what is VW then? It's the velocity of the wind, which is squared because we are talking about a pressure of a fluid over a surface. So in order to estimate the pressure, we need to square it and divide it by 2g. G is acceleration of gravity. Good. Now, what is the way we compute the velocity of the wind? We said that we need a probability distribution and a Gust factor. As an order of magnitude, it is recommended that you use a wind speed of measured over an interval of 30 seconds with a Gust factor of 1.2. So if you take wind measurements that are taken over an interval of 30 seconds, you have to use a Gust factor of 1.2. As I said, it's like a safety factor. The magnitude of CW depends on the shape of the ship above the water. Basically, as I said, it's an empirical coefficient, and also it depends on the orientation of the ship. Basically, what are the values recommended for CW? A recommended value is about 1.3. And if you have the wind against the bow, then you can take 0.9, so it becomes a reduction factor. But if you don't have, let's say, a convincing information, let's take it as a safety factor, and then let's take it greater than 1. Now, how can we compute AW and BW? These are specific behaviors of the ship. So you may have information from the manufacturer, from the producer, which give to you an estimate of the side windage area and the transversal windage area. And if you don't have any information, there are a couple of rules of thumb that you could use. And these rules of thumb suggest to estimate AW by multiplying the length between perpendiculars of the ship. And remember, we discussed it before. And times the sum of the G. G is the ship's freeboard, and plus Z, what is Z? The Z is the mean height of the transversal area of the, sorry, longitudinal area. AW is longitudinal windage area. This is longitudinal windage area. Good. BW, we can take a similar relationship. It's the product of B. B is the beam of the ship. Again, refer to the glossary if you have any doubt, which multiplies again G plus Y, and Y is the mean height of the ship, the mean height of the transverse area. I just would like to draw your attention on the fact that the worst condition from this relationship here, worst condition is when phi equal 90 degrees and phi is here. Namely, when the wind blows perpendicular to the transversal area of the ship. I think we can make a break now, 15 minutes. Do you have any question?
Yeah, I have a couple of issues I wanted to ask you, Professor.
Yes.
The first is that Professor Archetti told us that this course is like a consequence of an earlier course you did in the first semester.
Yeah.
And my question was, is it necessary to also do that part, or no, we can just go with Harbour engineering?
No, you can go with Harbour engineering.
Okay.
I am really not assuming that you attended my first course. By the way, it was only 12 hours, and so I am trying to be independent. And like, let me give you an example. Probability. I told you, you should know about it, but yeah. I'm not requiring at the exam and neither in my lecturing that you know more than probability with respect to just that it is an estimate of frequency.
Okay, in case we just do some research and we will be able to fulfill some little holes in our knowledge. And my second question was about the presentation. You said that it was a good idea to do in class. And if it's not like I don't need it now, but maybe if you could give some more details on how you would like this presentation.
Yeah, I think we can discuss briefly now, and I may say something more with respect to what I anticipated last time. What I said last time was prepare a presentation on a problem that you believe it's relevant to our teaching, and it shouldn't be something that overlaps with what I am lecturing. Your presentation should not substitute my lectures, but should be something more related, but more. And the ideal suggestion would be a case study. Like, let's suppose that you know of an harbor that has problems. Problems due to, for instance, mud siltation, and therefore they need to drag frequently, and they may have the problem of displacing the muds after dredging. And then you could explain what is the problem and what are the solutions, possible solutions that people have identified. Another problem may be a berth that needs to be maintained and recovered after maybe a storm, and maybe a storm that damaged the structure of the harbor, the structure of the berth, and you may report what happened and then the interventions that have been made. This is a second example. A third example, a student once presented the case study of an harbor in, I think it was in Indonesia, because the student was from there, and he knew that they had the considerable logistical problems. They weren't able to manage the traffic of the ship traffic, and therefore they devised some decision support systems they adopted a decision support system in order to manage the traffic. We are not talking about logistics, but it's indeed very important. It was a very nice example. The recommendation that I give to you, I give you two recommendations. First, your presentation must be technical, not really technical in terms of many equations, a lot of maths. This is not what we need, but it shouldn't be a simple report of an event like the one that we see at the TV, okay? Should be something more. So it should be addressed to an expert public, not to the person of the street. And otherwise, it's not really relevant for us. We are interested in technical details. This is the first recommendation. The second recommendation is duration. It should be short, like 5-8 minutes. So you understand that you can't go into very deep details, very refined details, but still I can tell you in 5-8 minutes you have plenty of time, and the number of slides should be like 5-8, something like that. Usually to students I give the recommendation, when you have to deliver a presentation, 1 slide per minute. This is a good estimate of the number of slides that you need. And the presentation may be delivered remotely or in physical attendance, and it's better in physical attendance. My aim is to stimulate a discussion afterwards. So the other students should, after your presentation, ask questions. And sometimes I oblige the students to ask questions. Usually I start, I break the ice, but then that's it. Is it clear?
Yes, yes. Thank you, Professor.
Okay, very good. I see that there is a fourth student, Rama. Are you there, or did you leave already for the break? You are there. Very good. Welcome. And I think, can I just ask you if you are in Ravenna or if you are in your country or remotely? We can't hear you. I don't know why, but no problem. Okay. Let's take the break now, and it's okay, 10 to 4, 5, 15 minutes. See you later. Okay, here I am. Now, couple of things that I forgot to say, and then we continue our discussion on the application of this formula that you see on the screen. First of all, there is one thing. When I explained why the sin and the cos are squared, I was not really precise and rigorous. There is a first multiplication by the sin and the cos, which is, as I mentioned, applied in order to estimate the component of the wind speed along the transversal direction. So, for instance, if you think at the figure that I made here, this figure here, basically you have this wind speed which you can decompose into components, this component and this component. And this is the component given by the velocity, let's say VW, I called it this way, cos phi, and this is the component VW sin phi, okay? And this, there is a second multiplication which is applied in order to introduce a correction factor for the friction, because actually the wind speed is transformed in a forcing through friction, and therefore there is the second multiplication which also takes into account friction, because in this way we take into account that when the real forcing is given by the wind speed multiplied by a friction. I hope I was clear. In any case, keep in mind that this is empirical. So you can see a physical basis, as I said, and the physical basis is given by the fact, for instance, that you see that in order to compute the pressure, the wind pressure, we apply a physical equation, a physical relationship, which is the relationship that gives the pressure exerted applied by a fluid that is hitting a surface. So we square the velocity and we divide by 2g, but then there are empirical corrections which are introduced through this factor CW, which is the wind force coefficient, and then through these multiplications that take friction into account. Another thing that I wanted to say, which I forgot to say, is the order of magnitude for the velocity VW. Okay, and I said that I gave an order of magnitude for the Gust factor, 1.2, when the data are measured over a time span of 30 seconds. And now I want to give an order of magnitude for velocity. And some guidelines recommend that the minimum velocity for computing mooring forces in exceptional situations, so extreme mooring forcing, should be, the minimum should be around 30 meters per second, which is, I mean, it's an extreme wind. If you think about the Bofford scale, 30 meters per second, it's an extreme wind, but still, of course, we are referring to extreme conditions. And 30 meters per second with a Gust factor of 1.2. And on the other hand, it is recommended not to exceed a wind velocity of about 40 meters per second, because if an exceptional event comes, as I said, usually ships are undocked, unberthed, or they take ballast in order to increase their stability. let's say that this operation of leaving the berth or taking ballast, it's usually taken when the wind speed exceeds 25-30 meters per second. So usually velocities around 30 meters per second are considered precautionary. Okay, and now let's talk about not here, just 1 second. Let's talk about I said empirical formulas for computing AW and BW. And so let's talk about the worst conditions in terms of the angle phi. So when, I said when phi is 90 degrees, we get the worst conditions. And in this case, when phi is 90 degrees, the relationship reduces to PW is equal to CW times AW times P, where P is basically this product here. Let me change the color. P is this product here. And these are the worst conditions. And on my website, you can find a figure. Let me see if I can copy it here, which gives, I think it is indeed interesting. You can find this figure, which gives an idea of, it gives an idea of the wind pressure for a given wind speed in the vertical axis this basically is computed, this wind pressure for phi equal to 90 degrees. And basically, you see two curves. One curve is given by a computation without taking the Gust factor into account. The curve below, which gives an higher wind pressure, it's a curve that it's computed with a Gust factor of 1.2. And this is an estimate of the pressure. So it's not the force, it's the pressure. It's the term that I highlighted in green here. Sorry. It's the term that I highlighted in green there. Let me just highlight them again. It's the term that it's highlighted in green in the relationship. And basically, it's you see the term P, lowercase p, is given just by the product of air density times wind velocity divided by the 2g. So you can understand it's just a function of wind velocity, which gives the pressure. And of course, to get the forcing, you have to multiply it by the wind force coefficient and the projection of the wind edge area. And what you see, basically, it's the progress of the wind force and the difference that you get by adopting a Gust coefficient of 1.2. I think that for wind forcing, I am done. And now I think we can move to wind loads. If you have any question, just step in. I recommend to you not to hesitate to step in if you have any question for me. And let me open a new window then in order to, yeah, please.
Can you hear? I have a question, not in this part, in the mooring lines.
Yes.
That you described. So it is like the interaction between the ship and the berth structure, as we talked. Okay, and this interaction involves only the water part, like when the ship is rotating or is entering our harbor. Okay. Excuse me for interruption. Yeah. Okay.
Yeah. So basically, I didn't understand. Do you have a specific question? No. I think the question was just
To clarify, yes.
What are the mooring lines? And I think I can paste here a picture that you can find on my website where you can find a schematic for a moored ship. And you see the mooring lines are the brown lines. And these are basically the ropes that we use to connect the ship to the berth. And so these are basically transmitting the forcing from the ship to the berth. So you have a forcing on the berth when the ship is moored through the mooring lines, or when the ship is mooring and it may hit the berth, or when it is mooring, they use temporary mooring lines in order to drive the ship. And in this case, still you have the mooring lines that are transforming the forcing, bringing the forcing from the ship to the berth. I'm not sure if I answered your question.
Yes, now understood. And if we have in smaller areas that we moor a ship to another ship, so this is like the same thing, and we try to move our loads to the surface, we could say.
Yes, that's true. That's true. Okay. I didn't understand. You said if we move the ship to another ship.
Yeah. Sometimes in marinas or smaller areas, we just we can have another ship next to the ship to the surface and just connect them.
Yeah, I understand. Yes. If you connect them in a way, you share the loadings.
Okay.
And especially it depends on the direction of the connection. But if it is a longitudinal connection, let's say that you share the loadings on against the transversal surface of the ship. And basically, the way you bring the forcings to the land is through the mooring lines that are connecting the land with the ships. And the mooring line that connects ship by ship, basically they, in a way, bring the loading from one ship to another ship. But in order to bring the loading on the berth, you need finally a connection between the ships. And I take this opportunity to clarify the nomenclature because I think it is important of these mooring lines. So the number one is called the headline to keep forward part of the ship against the dock. Keep in mind that usually we don't use all of them. This is an ideal connection that ensures stability. And the opposite action of the headline is given by the stern line that prevents forward movement. So through the headline and the stern line, you prevent forward and backward movement, and they are backed up by the number 3 and number 4, which are called forward spring, number 3, and aft spring, number 4. And again, these 3 and 4 mooring lines prevents the ship from moving back and forward. So they back up the headline and the stern line. And then you have 2 and 5. 2 is called the forward breast line, and 5 is the aft breast line. They keep the ship close to the pier, to the berth. So this is, I invite you, if you get an opportunity to go in a marina, just to have a look at the number of lines that they use. Of course, I mean, the heavier the ship and the more rigorous you have to be. Okay.
Okay, thank you.
Yeah, no problem. Just let me remove this figure here now because we don't need it. So let's talk about now the loads, the wind loads. Let me change the color because this is not really very visible. The wind loads. Now, sorry, this is not really clear. Loads. Okay, good. Now, basically the wind force is given by the product of the considered component of the wind pressure by the area of ship above water projected over the longitudinal and transversal plane of the ship. Keep in mind that the wind force has a direction, which is the direction of the wind. And the wind force may give rise to a component that is perpendicular to the ship center line and a component that is aligned to the ship center line. So basically, now we have to compute the load of the ship to the berth, because the load is transmitted through the mooring lines, as we said, and each mooring lines takes a portion of the load. So basically, we learned how to estimate the wind force, but now the wind force, which is a total. So let me just put again the sketch here. We have the wind force, which is the red one. This one. I put a black line. And then this wind force, we have to transform it in components along the mooring lines. This is what I anticipated we have to do if we want to make a very detailed design. So let me just change the color again. We have, according to this wind forcing, I understand, I can get that probably we have a force along line 6, which is traction. Okay, and then we have a force that is along line 3, which is traction, and we may have also some traction. It depends, but it depends on how they are, basically how the mooring lines are put under tension. But I understand that I would say that we may have some traction here and also some traction here, because the ship here tends to move forward. This is the tendency. I would say that the other mooring lines are not taking a significant load. And I also would say that the most loaded in this sketch, this is just my intuition, the most loaded are 3 and 6. And then less loaded. Less loaded 2 and 5. This is just my guess, let's say. But of course, in order to, we need a rigorous computation here. We need decomposition of wind forcing along the mooring lines. Good. Now, this is a quite complicated procedure. We will make an exercise, but you will see that it's nothing different with respect to a classical exercise of structural mechanics of vectorial decomposition, nothing more than that. And but we will make an exercise. In some cases, we may not need it because we could decide to compute the distributed loading. What does this mean? It means that we have this wind forcing. So let me just make another sketch here. This is the berth. And we have a wind forcing here over a ship. Wind forcing. Now, this wind forcing, we may simply say that it's transmitted to the berth along the length between the mooring lines. So if the mooring lines are fixed here, 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 and here, instead of computing any single force on any single bollard, we may say, okay, we have here a mooring length, let's call it LQ. I use LQ because it's the same symbol that I am using in my website. And let's decompose the wind forcing into components. And the two components are perpendicular wind forcing and the longitudinal wind forcing. Good. Now, and then we may say, let's call the longitudinal wind forcing PWX. And then we may say, okay, the wind forcing, let's call it the longitudinal wind forcing over the berth is distributed loading. So let's compute the distributed loading, longitudinal. Let's call it FDX. It's equal to PWX divided by LQ. This is very simple. And then we could call the perpendicular FDY equal to PWY divided by LQ. This is PWY. And this is a pressure. It's a pressure. It's not a traction in this case. Because, I mean, the wind forcing has, if we consider it as a whole, it gives a pressure against the berth in terms of perpendicular wind forcing. And then you may say, yes, but you, in the sketch that is on the right, you have shown that we may have some traction. Yes, we may have some traction because the longitudinal wind forcing may also originate some component of traction. And actually, I really don't know if the result is traction in the mooring lines 2, 3, 5, and 6. It may be that in some of them there is traction, in some of them there is not. But if I consider the distributed loading as a whole, I have a direction of the loading which is perpendicular and against the berth. It's not from the berth to the seaside. And because when I simplify, I consider only the distributed loading, I cannot consider very local forcing, local effects due by the inclination of the mooring lines, their direction. And therefore, this is a simplification that may bring us to, in a way, to a more simplified representation. There might be some forcings that we miss, but still, if the design is not very important, if the loads are not very important, we can simplify the situation by only taking distributed loading. And at this stage, if we take this assumption, we would be done. I mean, I have a berth structure with a longitudinal forcing and a perpendicular forcing, and I have all the information to design the structure and the foundations after wind forcing. I can compute the component of actions due to wind forcing. If I want, as I said, computation of point loads for each bollard, then I have to make this decomposition, vectorial decomposition, which I mentioned to you, we will do with an exercise, maybe next time. Perfect. If I have a pressure against the berth, the pressure is, of course, through the fenders. As I said, we have fenders between the berth and the boat. I am drawing the fenders in yellow. We have fenders which allow to calculate the forcing, the pressure from the wind to the boat to the berth. Now, this is, of course, a very simplified scheme. This is a long berth with a ship that is perfectly anchored. We may have some situations where we have to consider particular extra forcing that may happen. So, for instance, let me make this sketch. Let's suppose that you have a berth that has an angle, and the ship is berthed in this way. Sometimes this happens. And you have the mooring lines, which may be, let me change the color. Mooring lines, I'm not happy with this color, 1 second. Let's take this. I have a mooring line maybe here, and then a mooring line maybe here, and a mooring line maybe here, okay? And maybe a mooring line here. So we have to be careful because there might be after wind some rotation here, and therefore the ship may behave after wind, may take this position. Of course, we have to be careful about these possibilities and these possible local effects. Furthermore, there are other situations that we have to consider. For instance, for piers where ships can berth on both sides, we can assume that we can take a reduction factor, because if they can berth along both sides, there are some guidelines that say that the total wind load acting on the berth should be computed as the sum of the wind load on the largest ship plus 50% of the wind load on the ship on the other side of the pier. So there are local guidelines that you have to consult, because there might be specific situations which are not easy to interpret. So the scheme that I have drawn on this sheet is very simple. It's a situation that it doesn't present many question marks, but there are situations where we need really to make an effort to figure out what could happen during an extreme storm. And also you have to think that an extreme storm causes also extreme waves. So there is the combination between wind and waves that could really be a little bit tricky. Now, let me spend some words on vessel rotation, and let me open another page here. So let's talk about rotation here. Now, in general, keep in mind that the action of wind generates wind drift, and the drift is what is originated by the wind pressure, which causes, roughly speaking, a movement of the boat along the direction of the wind. If the boat was left free of moving, the drift causes a movement of the boat along the direction of the wind. But then we may have a rotational moment. So we have two components. We have the drift and the rotational moment. Okay, now we already discussed the drift, and we need to make a nice discussion if you want to study vessel rotation. And in particular, we need to define what is the pivot point for a ship. So what is the pivot point? The pivot point is the point around which the ship appears to be turning for an observer standing on board. So let's suppose that a ship starts to rotate. It is rotating around a vertical axis. And let's suppose that you are on board, and at a certain point you realize that you are standing vertically along the vertical axis, because you rotate, but you rotate around yourself. And the vertical axis is passing through your body. So this defines the position of the pivot point. And we may say that it's actually, it's not a point, it's an axis, but it's called pivot point. Okay. Now, it's called the pivot point. It's a technical term. Now, if a vessel is resting, it's not moving, intuitively you can get what I am going to say now. The pivot point, it's located in correspondence of the center of gravity of the underwater body of the ship. So basically, it's the ship is in a way anchored to the sea, to the water, through its underwater body. And the center of gravity of its underwater body, which includes maybe some load, some ballast, the center of gravity is the pivot point. If you basically provoke a rotation, the ship rotates around a vertical axis that is passing for the center of gravity of the underwater body, if the ship is resting. When the ship moves forward, the position of the pivot point shifts forward. And this is also something that you can get by intuition without the need of a complicated physical demonstration. So you get basically the ship moving forward, and then you have the pivot point that moves again forward. And for typical velocity of vessels, of ships, the pivot point will move to about 1/4 of the length of the vessel from the forward. Okay, when the vessel moves backward, then you have the pivot point shifting backward. So when is originated rotation after wind force? Under wind forcing, you can understand that. Let me make a very simple plot here, a very simple scheme here. So you have the sea, and you have the vessel that is standing in kind of this way. Let me just change the color for the vessel. Okay, and let's suppose that you have a windage area that is kind of this one. Okay, so we may say that the pivot point is around here. But the center of gravity of the side windage area is located somewhere, I would say, here. Okay, so if you have wind hitting the ship, yes. And basically, if I look from above, this is a ship that is can be seen like this, with the pivot point here, somewhere here, and 1 second here, and the center of gravity of the windage area here. So if you have wind coming from this side, you get a rotation of the vessel like this. Okay, because the vessel tends to rotate around the pivot point, and the forcing is eccentric with respect to the pivot point, and therefore you have rotation. And so rotation, of course, it's to be considered for a berthed ship because it causes some asymmetry in the distribution of loads. And we will see how we can take into account rotation when we will make the exercise that I mentioned to you. Rotation usually is taken into account when I am interested in computing the forces for each single bollard, and therefore it's something that it's not really considered when computing the distributed load, because of course in a way the presence of rotation may change the distribution of longitudinal and the perpendicular load over the berths, but it is usually not considered when we talk about when we only consider the distributed load. Okay, now I think with the wind forces we may close here. What is let me go back to my website. What is if we wanted to make a brief summary, what should we say now? Let me go to this page and go at the beginning. A brief summary of what we did, which may help you also to identify potential questions for the exam. So first of all, we talked about nautical terms related to ship size. Fine, this is a premise. So just be sure that you know what is the draught, what is the freeboard, what is the beam, what is the length between perpendicular, and what is the waterline length, etc. And then we talked about the Windrows. This is the second important issue that we discussed today. I don't think this is particularly complicated. You have links if you want to expand. Still, the interpretation of the Windrows requires some attention. And then we talked about estimation of probabilities from the Windrows, because actually we need probabilities to make our design. Probability of what? Of wind speed. And later on, we will need probabilities of wave height. And therefore, I mean, it's also important that you think about the association of the information from the Windrows and the concept of probability distribution, because through the probability distribution, you may estimate the extreme wind speed that you need to compute the wind forcing. And then we talked a lot about probabilities. And then we discussed about the Bofford wind force scale. Just remember what it is, because it is frequently used, this scale, in technical discussions. And then we talked about this empirical relationship for estimating the wind forcing and the force, the wind force. And then we talked about estimating the load on the berth. and we said distributed load and concentrated load in the bollards, and I said we will make an exercise on this. Very good. And then we talked about rotation. We didn't go into the details of rotation, but we highlighted that when we compute the loads, also the rotation, which is originated by a mismatch between the center of gravity of the wind edge area and the pivot point, needs to be considered. And this is what we discussed so far. I wonder whether you have any question. Good. By the way, before I continue, and if you have any questions, step in. Next Wednesday, in physical presence, if at least if the majority of you are booked in virtuale, sorry, in presente.unibo.it, I will lecture 2 hours, and the other 2 hours I will introduce practical exercises. I mentioned to you that I want to make some practical exercises by using open source software with you. So next Wednesday, the last 2 hours, I will introduce you to the open source and open software that I want to use. And we will consider, if we have time, the exercise of computing mooring forces bollard by bollard. This is the first communication that I wanted to give to you. Second, in order to clarify for today, I think I am lecturing up to 5:30, so we still have 40 minutes to go. Good. Now, you see that the next para in my tutorials is wave forces. Very good. Now, let me make a first premise by saying, and let me keep my website shared here, by saying that waves in proximity of ports have different behaviors with respect to waves offshore. I think that you have some experience on estimating the behaviors of ocean waves. But actually, when we get into ports, there is some interference between waves and structures. And usually there are also situations that are a bit complex for the interaction of the orography from the land and the wind. So you have very often, sorry, I forgot to say, you have some protections, because very often harbors, marinas are sheltered, protected by breakwaters, by other structures that aim to soften the waves. And therefore, I mean, the waves in the proximity of port are very singular ones, which result from the combination of ocean waves approaching the coast, and then they get impacted by, for instance, shoaling or some kind of reflection. And then you have locally generated waves by the boats, by the ships that are moving, and by local winds. And therefore, very often you need some specific monitoring. I mean, if the marina, the harbor is already existing, if the port is already existing, it is advisable that, and often it is done for important ports, it is always done. It is advisable that we set up a monitoring station, a dedicated monitoring station, in order to get experience on the specific wave regime, because as I said, it's more complicated than offshore. It may, usually in the ports, in the harbors, we don't have breaking of waves, but you know that waves may be suggested to breaking when approaching the coast. And in any case, they modify their shape. And so, I mean, the local condition needs to be carefully considered. Fortunately, we may see that the situation, I mean, the forcing from waves is not so relevant as the forcing from wind, as I anticipated. But and for this reason, when we compute the design wave, usually we take a relatively reduced wave height with respect to what we take, for instance, for designing breakwaters, for designing structures that are standing in the middle of the sea, because there are kind of mitigation of the wave height due to sheltering, etc. And also there is another thing to say that, as I said, given that the wave forcing is not so important, usually the berth structures are sized with respect to wind forcing, which is more relevant. And then, we can take the luxury of being less rigorous in estimating the wave forcing. As I said, if we have local measurements, they have for sure to be used. I think you already know what are the different forms of interaction and interference of a train of waves with infrastructures, with the coast. So I guess that you know what is reflection, what is refraction, what is wave shoaling, etc. At the end of the story, what we need to get is a design wave. So a design wave height, typically, because typically this is the most important information. Also, the frequency is important, but typically what is most important is the wave height, and for some kind of design, also the wave frequency. Wave frequency is important, not just for the forcing that originate on the ships and then the berth. We will see that actually it's not really considered wave frequency when computing wave forcing. Is not considered in the simple relationship, in the simple empirical relationship that we will consider. You will see that frequency is not considered. But when is frequency important? Frequency is important for the risk that resonance occurs between the characteristic frequency of the waves and the characteristic frequency of the moored ship. I try to better explain. Think about a moored ship and think of loading it with some weight. So you get the ship lowering into the sea. The ship is moored, and then you suddenly release the loading. Then the ship starts going up and down. And it goes up and down with a frequency that depends on the behavior, the structure of the ship, and depends on the position and material of the mooring lines. Because the mooring lines are always elastic. We want them to be elastic because in this way they are more resistant. On the other hand, if you think of anchoring a ship with mooring lines that are elastic, when you get this up and down, of course, elasticity of the mooring lines contributes to the movement. And as I said, there is a characteristic frequency of this movement of up and down of the ship. And if you get that the characteristic frequency is coincident, is very close with the frequency of the waves, you can get resonance. I think you know what resonance is. It's amplification of amplitude of the up and down movement until of course, the mooring forces are magnified to the extent that they may break the mooring lines or in a way give excessive actions on the berth. So this is why frequency is important. On the other hand, as I said, for the simple sizing that we often we often are required to make, we don't take frequency into account. Okay. Now, I talked about a design wave that we need. I think that you know how to compute a design wave height. I think that Professor Archetti already talked about it.
Yes, yes.
Very good. Still, in my website, you will find some discussion on probability and return period, and there is in-depth discussion of the relationship between probability and return period. I'm not asking anything related to that at the exam. I'm not asking anything related in my exam to estimation of design wave. I suggest you anyway to have a look to what is in my website, because I think there are some considerations that you don't know. And in particular, again, the relationship between probability, design life, and the probability that during a given design life, you may get a given wave height of a given return period. So the question may be, not at the exam, I mean, the general question may be, let's suppose that you design an Harbour, a berth for a return period of 50 years, and you get a design wave height. What is the probability that in 50 years you get the design wave height? So if the design wave height is estimated for a return period of 50 years, what is the probability that in 50 years I will get the design wave height? You may be tempted to say it's 1. No, it's not 1 because it's not certain. Nothing that is related to randomness is certain. So you don't have a probability of 1 of getting a design wave height with return period of 50 years during 50 years. This probability is 73%. So if you design a berth for a design life of 50 years, you take the design wave height with retro period of 50 years. During 50 years, you have 73% probability of getting that wave height, which I mean is not low. It's quite a huge probability. And there is a graph in my webpage that is explaining this concept, which is relevant for technical design. And then let's go to some rules of thumb of what may be a range for design wave heights to compute mooring forces for berthed ships. Okay, and you see the rules of thumb on my website. Good. Now, ships with up to 3,000 tons for a pleasure craft that is moored, take a design wave height of 0.4 meters. Fishing vessels with length overall less than 30 meters, design wave height 60 centimeters, 0.6 meters. Fishing vessels with length overall higher than 30 meters, high design wave height 1 meter. Other type of ship 1 meter. Ships with displacement greater than 3,000 tons, design wave height 2 meters. These are not numbers I will ask you at the exam, but just keep them in your mind to get a picture. Okay, as I said, you don't study for passing the exam, you study because you want to feel comfortable during a job interview, or even worse, during your professional career. So just try to figure out in your mind what are the orders of magnitude. Okay, now, so let's given for acquire the procedure for computation of the design wave height. Now the issue is how to compute the mooring forces, which I mean, it's not so obvious. First of all, we need a discussion on the movement of the ship. And we need a discussion about rotation, about what kind of movement a moored ship exposed to waves may suffer from. And so basically the ship is a body with 6 degrees of freedom, okay? And then it means that why 6 degrees of freedom? Because the ship can move along 3 axes, the 3 axes of the space. A ship can move along the 3 space coordinates. So it can move along X, it can move along Y, it can move along Z, along the vertical, along the transversal, along the longitudinal. In this figure, just one thing. In this figure here, you have, and just let me expand it a little bit. Just one second. Okay, very good. Now, in this figure here, you the X direction is the longitudinal, the Y direction is the transversal, and the vertical direction is Z. And these are 3 degrees of freedom, and then there are 3 rotations along the 3 axes. So you have 6 degrees of freedom. Let's talk about some terms. I think this figure is very nice. Just one second, and let me open it in a new. Okay, very good. So the 3 rotations, how they are called? The rotation top left, the rotation around the vertical axis is called yaw, okay? The rotation around the transversal axis is called pitch. The rotation around the longitudinal axis is called roll, okay? Good. So we have these 3 possible rotations. Now, you know that first of all, you know that we apply very frequently empirical relationships. Okay, very good. And so let me jump directly to the description of these 2 empirical relationships, but let me refer, I want to write them down on the graphic blackboard. Just one second, because I think it is more productive is if I am, because one thing that I often suffer from is excessive speed. So if I write, I think I can control my speed better. Once again, let me emphasize that these are empirical relationships, just to be used for, I mean, either a preliminary design or the design of structures that can allow some approximation. And so let me just write down the formula for the transverse wave force in kilonewton. In my website, I call it as FT wave. By the way, just a premise. The relationship for computing the wind force that I mentioned before, just please learn it by memory. There are, I don't think I will ask you many things to learn by memory, but the relationship for computing the wind force, which is not, I don't think it is difficult to learn by memory. Just please remember it. And also, if you could make an effort to remember these 2 empirical relationships that I'm writing now, I think it would be helpful, because I think that this helps you to remember also the concept. And so just take a note that I may ask at the exam these two relationships, then the relationship for computing the wind force, and then the relationship for computing the lateral or transverse wave force. So Ft wave, where T stays for transverse, it's given by the product of CFW. It is called water plane coefficient, depends on the wavelength at the location of interest and the ship's draught. And there are some suggested values for this coefficient, which you can find in my website. You don't need to remember, of course, the suggested values. Now, there is a second coefficient, which is called depth coefficient, depending on the wavelength again, and the water depth at the location. Again, there are some suggested values in my website. And then you have the specific weight of water, and we get into the physical part of it here. And then we have the wave height square, y square, because it's the forcing is related to the wave energy, and the wave energy depends on the wave height, as you know. And then we have a coefficient, a term called d prime, what is projection of the ship length in the direction of the incident waves. And this is a transverse force, so you don't have to be surprised if we compute it in as a function of the ship length. By the way, also the longitudinal force is computed as a function of the ship length, as you will see, because in this case it's friction that comes into play. And then it's multiplied by sin square phi. Phi, it's the usual angle that I introduced when introducing the relationship for computing the wind forcing. Now, what about FL wave, the longitudinal forcing? We have again CFW. We have again the same relationship, so CDW, and then we have gamma W, and then we have HS square times d prime, the second, but it's multiplied by cos square phi. Okay, please make an effort to remember. And you pass the exam anyway if you don't remember them, but I think it's much better if you make an effort to remember and with the meaning of the coefficients that I introduced. Now, of course, as I said, there are suggested values for the coefficient in my website. We don't need to discuss them. I just want to show you one thing. I pass to my website just to show you where you can find them. So these are two figures which I took from the Ports Designer Handbook, which give you CFW and CDW depending on the horizontal axis, where you see that there is this relationship where in the caption you can find what is H is water depth at the location, what is D, which is the draught of the ship, and what is LW, which is wavelength at the location. Perfect. And that's it. Just 1 second. I just want to give you a couple of orders of magnitude. So more than orders of magnitude, some considerations that help you to figure out what is the behavior of the mooring forces arising from wave forcing. So mooring line forces are induced almost entirely by waves of period longer than 20 seconds, with major contributions occurring in the period range 40 to 100 seconds. Rolling is triggered primarily by swells with period in the 13-19 seconds range. Just to remind you, rolling is this one, rotation along the longitudinal axis. Now, pitching is small and insensitive to the wave period usually, whereas heave motions, let's see what is heave just in a second, tend to equal the wave height at long periods and are smaller with short period waves. What is heave here? These are the translations. You can call it sway, top left. It's translation along the transversal direction. Surge is the move along the longitudinal direction. The heave is the movement along the vertical direction. So let's read again the third point. Pitching is small and insensitive to the wave period. So pitching is not really a matter of concern, while heave motions tend to equal the wave height at long periods. This is also intuitive. If you think at a wave with a long period, then it's by intuition you can get that heave can tend to be equivalent to the wave height, while it's smaller when short period waves occur. Okay, so as I said, these relationships are empirical relationship. What if we want to get a better estimate, something more refined? It is not easy because, as I said, these are random processes. These are processes that it's difficult to predict in detail. There is turbulence, there is randomness, as I said, which combined with turbulence also originates chaos. Chaos means that sometimes they become unpredictable. The result of different train of waves crossing each other and interfering with infrastructures, interfering with the effect of orography and therefore local winds may become impossible to predict. What it is frequently done, and this is what I wanted to mention to you, is estimation when the project is really important, estimation through physical modeling. What is physical modeling? It is small scale modeling. Small scale models are built in the lab. They are often called physical models. And I want to give you an example. There is in my website a video, and let me just show you this because it's very nice. And let's skip this ad. Just 1 second. Okay, and it is just enough if you have a look, and the audio is not important. This is a description of a basin, and the audio I am translating, where small-scale models are run. And you see that there is a wave generator here. You see this structure that is moving is a wave generator, which can originate waves. It lasts 5 minutes, so I don't want to see all of it. Let me jump backward, and these are the technical specifications. You see that there are the characteristic of waves that can be generated. And here you see an example of application. And here they are testing some groins, some protections for Harbour basins. You see here the protections, and they are trying to see with a small scale model if the protection resists against waves. And here there is another application with the wave generator. I think they are studying here the effect of waves on coastal erosion and on coastal protections. I think this is what they are studying here. And then here you see another example of application. You see the effect of waves over an harbor. And this is how complicated the projects are dealt with. And the lab of Deltares, where I took these videos, is an institute, a research institute in the Netherlands, close to Delft, where they make these kind of experiments, and where they make also real world and full-scale models, meaning that sometimes in certain locations they make experiments. They try innovative structures for protecting the coast and the harbors, or they try innovative kind of berth structures. It is definitely interesting. I think there are some interesting videos on their website also where they try to simulate the effect of monster waves or rogue waves. What are these kind of waves? In open ocean, sometimes it happens that a combination of different train waves gives rise to a single monster wave, which is dangerous even for the heavier ships. There is a Wikipedia page linked in my website if you are interested. In the past, they thought that these rogue waves were a kind of myth, and they were not actually occurring. Recently, with the help of innovative sea wave monitoring, we realized that indeed in the open ocean it can happen that these monster single waves form up. And the reason why they indeed are originated are still not known, but it is probably, most probably, the nonlinear interaction between different train waves that give such an effect. And it looks like they were responsible for the drowning, for the sinking of ships that in the history disappeared. You can look also on Wikipedia, a list of the ships that for which we have memory about their sudden disappearance. They disappeared in the open oceans and were never found. And in some cases, they have been probably caused, these accidents have been probably caused by rogue waves. Now, I just want to say that we still have to talk about the load by currents. It's a marginal discussion. We have almost done. We will talk about it the next time because I don't want, I think today I lecture already enough. And but before finishing, I want to take these 10 minutes to give you some preliminary information that will allow us to save time next Wednesday when I will introduce to you some computational exercises. But before I take these 10 minutes to discuss this, I wonder if you have any question for me.
Yes, just a quick one. I couldn't understand the name of the big waves, the single big waves, yeah. How they are called?
Yeah, you see here, I have a box in my website.
Okay, rogue wave.
Rogue wave, yeah, or monster wave, and or mega waves. But there is here a link, Wikipedia, and freak waves, monster waves, episodic waves, and it's very interesting. So have a look. It's not for my exam, and also it's not really for harbors because they form in the open ocean. But if you go in my website, but I think also here, you see they were considered a myth in the past. You see these pictures. I think there is a picture here. Here there is an interesting graph. You see the rogue wave here. There's a single one with an amplitude that is more than twice the amplitude of the other waves into the train. It is interesting, but still there is not much information to study them. They are the subject of active research. You see, this is a simulation in the lab, I think, where they are trying to form it. And let me go back to my website, because here there is an interesting picture. Yeah, it's in Wikimedia Commons, rogue waves. And this is a picture that is put over a berth, and therefore it's not really a warning. But if they put the picture here, it's probably because they are also concerned that you know, possibly they may form also in proximity of the coast. Okay.
I did in my bachelor, I did a thesis on soliton waves. And they are very particular, and yeah, it's very interesting.
Yes. Where did you take your bachelor? In Bologna or?
No, I did it in Politecnico in Milan.
Ah, okay. I see. I see. Interesting. Okay. And now let me just close. Other questions? No? Okay. Let me just give you the screen is shared. So let me give you the information. First of all, if you go back to the website of the course, you see that there is here tutorial web page for the practical exercises. The software that I want to use is R and RStudio. Let's focus on R first. And what I suggest to you, I kindly ask you, is to install the software on your PC before next Wednesday. And next Wednesday, if we dedicate a couple of hours to that, I think we will only be able to learn using it and not to go to make the exercise. But let's see how we can download and install it. It's very simple. First of all, you may go to Google. Just 1 second, Google. Perfect. And in Google, I have to take the keyboard closer to me, otherwise. In Google, you should look for R. I suggest R project, R-project. You may also look for R package. Let me see if we can find it, or R package. Yes, and you get to the first link, the R project for statistical computing. Actually, don't be concerned by the word statistical, because this is a software for making computation. And I think you have some experience with MATLAB. Can I ask you if you have also experience with R? Okay, nobody. But I think you have experience with MATLAB. They are very similar. The difference.
We have, Professor, we had some courses with you last semester.
Okay, and so you know R already. Perfect.
Yes,
yeah,
a few.
Okay. Yeah, it's okay. Now, if you go on the link here, as I said, it's similar to MATLAB. The difference is that this is free and open source. So it's accessible to you anytime. It's in MATLAB, you know that you can use it only to the campus, etc. So MATLAB is commercial. So if you get to the web page, go to download. First, okay, go to download, and you have to click on CRAN, and then you select a cloud, whatever it is. Usually I take Austria, but you can select whatever you want. Download R for Windows, and then you need to download only the base. Okay, so if you go here, download R for Windows, and then you get the download starting, and then you just have to double click on it. It's very simple. Okay, and what I kindly ask you to do is to just install it. You don't have to run it, just install, and then just click on it to see if it starts. And then if it starts, then the first steps, we can make them together. Now, if you attended already with me, let's say that the first lecture next Wednesday, probably it's a repetition for you, but I don't think you will get annoyed or bored. But anyway, I just wanted to point out that it's basically the same introduction that I will make. When you get to the download page, you see that there is documentation manuals. What I suggest is to download the first one, an introduction to R. I think it is the same manual that you find linked on my website, I think. I'm not really sure because maybe that on my website there is a previous version, but I don't think they made a lot of changes. And then you can take the PDF. And this introduction is very nice. I mean, it's not a long manual, and it gives, I think, all what you need. But actually, you shouldn't need anything because we will start working on that together. And but we will save some time on Wednesday if you have it already installed. Okay. Any question?
No.
Okay. Thank you, grazie. If you have any suggestion to give to me, like I am too slow, I am too fast, I don't know what, just let me know. As I said, you can send an email if you prefer not to speak with the other students present, but I really would appreciate your feedback, either if it is positive, negative, it's useful for me. Okay, so students, thank you very much. Let me just, before we say goodbye, let me stop the recording, and the recording of last time is already available in the playlist.